Hello and welcome. In this explainer, we're diving into what is, without a doubt, the most important invention of the 20th century. I'm talking about the transistor. It's this tiny, tiny switch that literally powers everything in our digital world. And we're not just going to talk about the invention itself, but also the mind-blowing exponential law that dictated its growth and really shaped the world we live in today.
All right, so here's our game plan. We're going to start at the very beginning with that revolutionary spark. Then we'll see how silicon became the bedrock for all of this. After that, we'll get into the wild challenge of cramming more and more of these things onto tiny circuits, which, you guessed it, leads us straight to the legendary law of Moore. And we'll wrap it all up by looking to the future and asking, well, what's next?
So, to really get why this was such a huge deal, you got to understand the world before the transistor. Imagine electronics run by these big, clumsy vacuum tubes. We're talking fragile glass bulbs that got super hot, ate up tons of power, and were just massive. They were the clumsy giants of their time, and they were about to be taken down by a tiny, tiny revolution.
Yeah, check this out. Before 1947, your only option for controlling electricity was a vacuum tube. They were huge, they were power hogs, and frankly, they burned out all the time. But then, bam, Bell Labs comes along with this solid-state device. It was ridiculously small in comparison, sipped power, was way more durable, and the speed? It could switch signals faster than anything they'd ever seen before. A total game changer.
Okay, so what is a transistor, really? Well, think of it as a microscopic light switch, but here's the magic. It has 0 moving parts. On December 23, 1947, 3 guys, John Bardeen, Walter Brattain, and William Shockley, showed it off for the first time. This little thing could either boost a signal or switch it on and off with blinding speed. And that simple on-off capability, that became the fundamental atom, the basic building block of our entire digital universe.
And just look at how fast things moved. Seriously, in a little over 10 years, they went from this clunky, fragile prototype to a much tougher design, and then to something they could actually mass produce. You had the switch to silicon in '54, which was huge. But then, 1959 hits, and it's a double whammy. You get the planar process for manufacturing and the invention of the MOSFET. Those two things together, that's what really kicked the doors open for the digital age.
You know, even the name has a cool backstory. The folks at Bell Labs couldn't decide what to call it, so they literally held a vote. The winning name, Transistor, came from an engineer named John R. Pierce. And it's perfect, right? It's a mashup of transfer and resistor, which is exactly what it does. It transfers a signal across a variable resistor. Pretty clever.
All right, let's move on to the foundation of all this, the material itself. Now, you might be surprised to hear that the very first transistors weren't made of silicon. Nope. They used a different element, germanium. But the real future, the thing that would build our entire digital age, was built on something way, way more common. I'm talking about sand. So here you've got the showdown. Germanium versus silicon. Germanium was the early favorite, but silicon came in with 2 knockout punches. First, it could handle way more heat without failing. But the real secret weapon? Silicon naturally forms this perfect, stable, protective layer of, well, glass, basically. Silicon dioxide. And that little trick would change everything. And then there's this. Why did silicon win? It's everywhere. Silicon makes up a whopping 28% of the Earth's crust. It's in the sand on the beach, it's in the rocks in your backyard. It is dirt cheap, and there's an almost endless supply. You can't build a global technological revolution on something rare and expensive. You build it on sand.
Okay, so remember that protective layer of glass I mentioned? Here's where it gets genius. Scientists at Bell Labs figured out that this layer didn't just protect the silicon, you could etch tiny patterns into it and use it like a stencil. This let them control exactly where they put impurities into the silicon. This whole idea became the planar process, building transistors on a flat surface, like you're screen printing a t-shirt, and that was the breakthrough that made mass production possible.
Okay, so we've got the perfect material, silicon, and we've got a way to mass produce stuff on it. So what's the next big hurdle? Scale. It's one thing to build a transistor, but how in the world do you cram thousands, then millions, and now billions onto a tiny sliver of silicon?
The answer, the hero of our story, is the MOSFET. Invented back in 1959, this thing was an absolute masterpiece. First, it was ridiculously easy to shrink down, and second, it barely used any power unless it was actively switching. It's like a light that's off until you flip the switch. That low-power design was the key to packing them together by the millions without melting the whole thing.
So the MOSFET had it all. You could pack them in super tight, they didn't get hot, and they were lightning fast. You combine that amazing design with the planar manufacturing process, and you get the integrated circuit, the microchip. An entire complex circuit with all its components all built on one tiny piece of silicon. The modern world was born right there.
Now, get ready for a number that's going to break your brain. We humans have made an estimated 13 sextillion MOSFETs. That's a 13 with 21 zeros after it. Let that sink in. It is by far the most produced object in all of human history. More than bricks, more than nails, more than anything. They are the invisible bedrock of, well, everything. Your phone, your car, your coffee maker, everything.
Now, this explosion in numbers, this relentless shrinking, it wasn't just a happy accident. It turns out, for decades, the entire industry was following a roadmap, a kind of prophecy laid out by one of its founders back in 1965.
So this guy, Gordon Moore, who would later go on to co-found Intel, was writing an article, and he noticed a pattern. He saw that the number of components they could fit on a chip was doubling pretty much every single year. So he put it out there as a prediction, and that simple observation became the legendary Moore's Law.
Now, a decade later, in 1975, he updated his forecast. He tweaked it to say the number of transistors would double about every 2 years, and that's the version that stuck. But here's a super important point people get wrong all the time. Moore's Law is about the number of transistors, the density. It's not about performance doubling every 18 months. That was a related idea from someone else at Intel. It's a subtle but key difference.
And that brings us to the most crucial thing to understand about Moore's Law. It wasn't a law of physics, right? It was more like a challenge. It became this self-fulfilling prophecy for the whole industry. It was the goalpost, the target everyone aimed for. It forced companies to pour unbelievable amounts of money and brainpower into figuring out how to hit that next goal on the curve, year after year.
But you can't cheat physics forever. Exponential curves can't go on to infinity. And after more than half a century of this incredible ride, we're finally bumping up against the hard physical limits. Transistors are now so small, just a handful of atoms across, that the strange, weird rules of quantum mechanics are starting to mess things up. Which of course leads us to maybe the hottest debate in all of tech right now. Has the engine finally stalled? After powering our world for 50 years, is Moore's Law finally, actually, dead? And the crazy thing is, the people at the very top can't even agree. You've got Jensen Huang, the CEO of NVIDIA, saying flat out, Moore's Law's dead. He says it's just too hard and too expensive now. But then you have Pat Gelsinger, the CEO of Intel, pushing back and saying, nope, not dead. He believes we can keep the dream alive with clever new designs and ways of putting chips together.
So whether the classic law is dead or just on life support, the future is something the industry calls more than more. The idea is, if you can't build smaller, you have to build smarter. Instead of just making things flat, we're going 3D. We're getting new transistor designs that wrap around themselves. We're literally stacking chips on top of each other. We're looking at new materials to replace silicon and even exploring totally different ways of computing, like quantum and brain-inspired chips.
So when you think about it, the journey has just been unbelievable. From one single clunky device in a lab back in 1947 to sextrillions of invisible switches running our entire civilization. The transistor didn't just change the world, it built the modern world. And that leaves us with the big exciting question. Thanks for watching.